Section 4.1, Related Rates. First, let's discuss what a related rates problem is. A related rates problem is a problem where the rate of change of multiple variables are related to each other. Oftentimes, these variables will depend on a common independent variable, which will usually be time. Doesn't always have to be time, but it usually is. Below will be an example of such a related rates problem. Suppose a balloon is filled with air at a constant rate of 2 cubic centimeters per second. How fast is the radius of the balloon increasing when the radius is 3 centimeters? Let's start talking about why this is a related rates problem. If we reread the problem, we see terms such as constant rate and fast. Those terms are associated to rates of change. Now, how can we relate those rates of change together? If we are filling a balloon up with air, that means we are changing the volume of the balloon. And balloons tend to be spherical. Recall that V equals 4/3 pi r cubed is the formula we would use to find the volume of a sphere. Since they tell us that the balloon is being filled with air at a constant rate of 2 centimeters squared per second, this would be the rate of change for the volume, which would be dV dt, where t represents time since the volume is changing over time. So dV dt would equal 2. They're also asking how fast is the radius of the balloon increasing. R represents our radius, so how fast the radius is changing would be dr dt. And the dt is because our radius is changing over time. Well, from what we see so far from the volume formula for a sphere, I know how to relate the volume to the radius. But how do I relate these rates? Because the radius and volume are changing with time, both v and r are functions of time. Using what we learned about implicit differentiation, we can proceed to differentiate both sides of this equation with respect to time. Even though I don't see t in the equation, I can still use the implicit differentiation. The derivative of v with respect to time would be dv dt. As for the derivative of the 4/3 pi r cubed, applying power rule, we get 4 pi r squared, and then due to the chain rule with r being a function of time, we multiply by the dr dt. Now I have an equation that relates the rate of change of volume to the rate of change of the radius. How do we use this to finish answering our question? My goal is I'm trying to find dr dt. I know dv dt, but I'm missing r, the radius of my balloon. The problem is asking us to find the dr dt when our radius is 3. So here we're going to set r equal to 3. And now we can plug in our values. And now we have an equation to solve. When we solve for the dr dt, we get that dr dt would equal 1/18 pi. As for units, whenever we're finding the units of a derivative, it will always be the units of the dependent variable divided by the units of the independent variable. The radius is measured in centimeters, and from our rate at which our volume is changing, we can tell that the time is being measured in seconds. So our dr dt equals 1 pi over 18 centimeters per second, which means our answer to the question of how fast is the radius of the balloon increasing, that would be 1/18 pi centimeters per second. Looking back at the problem we did in example 1, we can come up with a strategy to help us solve related rates problems. The first step is to assign symbols to all variables involved in the problem. Oftentimes it will help to draw a picture of some kind, especially for geometry-based problems. In the last problem, we used V for volume and R for radius. We didn't draw a picture because it was just a simple balloon or sphere that we were using. Step 2, you want to state in terms of the variables the information that was given and the rate to be determined. So here, you're just going to assign whatever variables you can value, and then try to determine any values of the derivatives of those variables. Similar to what we did in the previous problem, where we assigned dv dt the value of 2. From there, you're going to find an equation that relates to the variables that were introduced in step 1. In our last example, that was the volume of a sphere formula, v equals 4/3 pi r cubed. For most geometry problems, there is an already established formula that can be used, for example, the volume of a sphere. Oftentimes, if you don't know these formulas for geometry, you can always look them up. Another thing to keep in mind, you may need to use more than one equation. We'll see an example of that later. After you find your equation or equations, you want to differentiate both sides of the equation implicitly with respect to the independent variable. This new equation will relate the derivative of those variables. Once when you have your derivative, you will be able to substitute all known values into the equation, then solve for the unknown rate of change. There may be times where you'll need to go back to the equation or equations in step 3 to help you find any missing variables. We'll see an example of that later on. To help us better understand steps 4 and 5, let's take a look at the following problems where steps 1 through 3 are already done for us. Our first problem, we're told that y equals cosine of x plus 5 and dx dt equals -2, and we're trying to find dy dt at x equals pi over 4. Here, we see that x and y have to be functions of time, since dx dt and dy dt represent the rate of change of x and y respectively over time. So we'll start by taking our derivative implicitly with respect to t. The derivative of y with respect to time is dy dt. As for our right-hand side, the derivative of cosine x with respect to t is negative sine x dx dt. The dx dt coming from chain rule. The derivative of 5 is 0. Now our goal is we're trying to find dy dt. Looking at our known values, we know dx dt, we know x, so we do have everything we need to find our dy dt. When we plug in our values, we get dy dt equals negative sine pi over 4 times -2. Sine pi over 2 is root 2 over 2. Negative root 2 over 2 times -2 would be positive root 2. So our dy dt would just be root 2. Since dy dt is positive, that does tell us that at this moment, our value of y would be increasing. In the next example, we're told that z squared equals y e to the x, and dy dt equals 2, while dz dt equals 3. We want to find dx dt at y equals 4 and z equals 2. So from the three derivatives that we have, we see that z, y, and x are all functions of t. So we'll take our derivative of our equation implicitly. For our left-hand side, the derivative of z squared with respect to t will be 2z dz dt. As for the right-hand side, y and e to the x are both functions of t. So we have to use product rule. In our product rule, we would take the derivative of our first factor y first, which is dy dt, times our second factor, e to the x, plus, now we keep our first factor, y, the same, but we take the derivative of e to the x with respect to t. For the exponential rule, we get e to the x times dx dt. Our goal is we're trying to figure out dx dt. Looking at what we know, we're told the value of z, we're told the value of dz dt, we're told the value of dy dt, and we're told the value of y. And our goal is we're trying to figure out the dx dt. The issue I have now is there's one variable I do not know yet, and that is x. If I know x, I'd be able to use our related rates equation that we just found. This is what I was describing in the last note of step 5. Sometimes we may need to use the original equation to help us figure out any missing variables. If we look at the original equation, we know z, we know y. So I have everything I need to solve for x. So using this equation, we have 2 squared equals 4 e to the x. If we solve, divide both sides by 4, keeping in mind that 2 squared is 4, we get 1 equals e to the x. Writing in the equivalent logarithmic form, we get that x equals the natural log of 1, which is equal to 0. Now we figured out the value of x, and we have everything we need to solve for dx dt. From our related rates equation, we can plug in all of our values, and we get 2 times 2 times 3 equals 2 times e to the 0 plus 4 times e to the 0 dx dt. Now to solve for dx dt. Start off by simplifying where we can, subtract 2, then divide by 4, and we get dx dt equals 5/2. Suppose a 25-foot ladder is leaning against the wall of a building. The base of the ladder is sliding away from the wall at a rate of 2 feet per second. How fast is the top of the ladder sliding down the wall when the base is 10 feet away from the wall? To start off the problem, we should draw a picture. The horizontal line that I drew in blue will represent the ground. The vertical line I drew will represent the wall. And unless told otherwise, we will always assume walls are perpendicular to the ground. And this green line will represent our ladder. Since the base of the ladder is sliding away from the wall, we should make the distance between the wall and the base of the ladder a variable. We'll call this distance x. As the base of the ladder slides away from the wall, the top of the ladder is sliding down the wall, which means the distance from the ground to the top of the ladder is also changing. We'll call this value y. As for the ladder itself, the ladder is not changing length. That will stay a constant 25 feet. What I've just drawn now allows me to visualize how I should relate the new variables I've just made. Since x, y, and 25 represent side lengths of this right triangle that we see in the figure, I can relate them using Pythagorean theorem. That is, x squared plus y squared equals 25 squared. Now that I have my variables related in an equation, I can take the derivative of this equation with respect to time, since x and y are both changing over time. The left-hand side will be 2x dx dt plus 2y dy dt. As for the right-hand side, 25 squared is just a number. You could evaluate it if you want to, but its derivative will be 0. So now we have a related rates equation. Going back, let's think about the values of our variables. In the problem, other than knowing that the ladder is 25 feet long, we know that the base of the ladder is sliding away from the wall at a rate of 2 feet per second. The x dt would represent the rate at which the base of the ladder is sliding away from the wall. Since the ladder is sliding away from the wall, that means x should be increasing. So our derivative will be positive. As for the quantity, it would be 2. Make sure you are careful with signs. If the variable is increasing, the derivative should be positive. If the variable is decreasing, its derivative should be negative. dy dt is unknown and is the value we're looking for. And we're looking for dy dt for when x equals 10, since they tell us we want to know how fast the ladder is falling when the base is 10 feet away from the wall. If I take a look at my related rates equation, I know x, dx dt, and dy dt. The problem is I need to figure out y. To figure out y, I will use our original equation. We'll take our value of x and plug it into our equation. Now we can solve for y. And when we solve for y, we get y equals plus or minus 5 root 21. However, y is supposed to be a positive value since it represents the distance between the top of the ladder and the ground. So our y should be positive 5 root 21. Remember, whenever you take the square root of both sides, do not forget the plus or minus. Determine after you solve for y whether your answer should be positive or negative. Now that we have our missing y, we can go ahead and solve for our dy dt. Plug in our values. Now we can simplify the equation, then subtract over 40 and divide by the 10 root 21. And when we do, we get negative 4 over root 21 or negative 4 root 21 over 21. Now to answer our question, and this is where we have to be careful with the interpretation. The wording of the problem already tells us that the ladder is sliding down the wall, which means our value of y should be decreasing. So to answer our question, how fast is the ladder sliding down? We'll just simply say 4 square root of 21 over 21, since the question is already telling us our derivative should be negative in the first place. Suppose water is draining from a funnel that is the shape of a right circular cone whose base has a diameter of 10 inches and a height of 15 inches. Water is draining from the funnel at a rate of 0.01 cubic inches per second. How fast is the height of the water in the funnel decreasing when there is 30 cubic inches of water left? We should start by drawing a picture. We are told that our funnel is a right circular cone. Since funnels are cones that are upside down, we will draw this upside down cone. We're told that the diameter, which would be the diameter of the opening of the funnel, is 10 inches, and the height is 15 inches. We are told that water is draining from the funnel. We'll let the blue region that I've just drawn inside of our funnel to be the remaining water. Note that water is a liquid, and liquid will take on the shape of its container. So our water will also be in the shape of a cone. Since we want to know how fast the water level is decreasing while water is draining, we should focus on the volume of a cone. The formula for calculating the volume of a cone is V equals 1/3 pi r squared. H would be the height of the water. R would be the radius of the circular base of our water. Here, R, H, and V are all changing with time, because as the water drains, we can see that the cone of water will get smaller and smaller, causing the radius to get smaller and the height to get smaller. So when we differentiate with respect to time, we have that dV dt would equal 1/3 pi is a constant multiplier. As for the r squared h, since both r and h are functions of time, we must apply product rule to differentiate. First, the derivative of r squared is 2r dr dt. Keep h the same, plus we'll keep r the same, and take the derivative of h, which would be dh dt. Now let's see if we can assign any values. We do have to be careful with the 10 inches and the 15 inches that are provided in the problem. They tell us about the dimensions of the cone, not about the water. We are only concerned with measurements of the water. We are told that water is draining from the funnel. This would indicate that there is a dV dt. So we're told that dV dt would be negative since the water is draining, 0.01 because of the rate. We want to figure out how fast the height of the water, which is dH dt, is draining when the volume is 30 cubic inches. The problem is if we look at our dV dt equation now, the only variable we know is dV dt. We're looking for dH dt, but we don't know h, r, or dr dt. So let's back up and see if we can find another relationship with r and h that can help us. If we take a closer look at our figure, we can see for the water, the height and the radius make a right triangle. The same thing goes for the funnel. Since the diameter of the funnel is 10, then the radius of the funnel is 5. And we can see that the height of the funnel and the radius of the funnel also make a right triangle. And we see that the right triangle formed for the water is nested inside of the right triangle formed by the cone. This means this angle at the point of our funnel would be common with the two triangles, which means the other two angles that are not in the point or the right angle would also be equal. This tells us that the two triangles formed by the height and the radius of the two respective cones are similar, which means the ratio of the radius to height of the water cone is equal to the ratio of the radius to height of the funnel. Since we're concerned primarily with dH dt, we can solve for r in this secondary equation, and we get that r equals 1/3 h. We can take this second equation and plug it into our volume equation, and we get that v equals 1/27 pi r cubed h. Unlike before when we had r and h's, we can now differentiate without needing the product rule. The left-hand side would be dv dt. The right-hand side will become 1/9 pi h squared dH dt. So we were able to reduce the number of variables for the dV dt formula from 4 down to 2, which would be the h and the dH dt. But I still don't know h. Since we have volume completely in terms of h, we can now use that formula to solve for h. V is 30, and we have that 30 equals 1/27 pi h cubed, which means h equals the cube root of 810 over pi. Now we can set up our equation to solve for dH dt in our volume equation. We have the equation negative 0.01 equals pi over 9 times the cube root of 810 over pi squared times dH dt. Divide both sides by what's being multiplied to dH dt, and we get that dH dt is approximately negative 0.045. As for units, it would be inches per second. So to answer the question, which we'll put here at the top, how fast is the water level decreasing? The decreasing already implies that the derivative should be negative, so the answer would be 0.045 inches per second.